I want to tell you about an experiment that has never been run, not because it is technically impossible, not because it requires technology we do not have, but because nobody in the history of physics has ever tried to observe with the full precision of our best instruments and our best theories the exact moment at which a living system ceases to be alive. We have watched stars collapse. We have tracked the decay of individual subatomic particles to within fractions of a nanosecond. We have measured the temperature of the universe to 7 decimal places. We have detected gravitational waves produced by black hole collisions a billion light years away. We have done all of this with extraordinary precision and extraordinary care. But the moment of death, the transition from living to not living, from being to not being, has never been subjected to the kind of rigorous physical analysis that we apply to everything else. And when you ask why, when you really press on the question of why physics has never looked directly at death with the same precision it brings to everything else, the answer you get is not that the experiment is too hard. The answer, buried underneath the technical deflections and the disciplinary boundaries and the cultural discomfort that surrounds the subject, is something more unsettling. The answer is that when physicists do look carefully at what death would have to mean at the level of fundamental physics, they find something that does not fit the framework, something that the equations do not accommodate in the way the intuition expects, something that suggests the boundary between being and not being is not where we think it is and may not be the kind of boundary that physics recognizes at all. Let me be precise about what I mean, because precision is the only thing that separates this conversation from philosophy or theology or wishful thinking. I am not going to tell you that death is an illusion. I am not going to tell you that consciousness survives the death of the body. I am not going to make promises that the physics cannot keep. What I am going to do is show you what the physics actually says when you ask it directly. What happens to the information that constitutes a living system when that system stops functioning? And the answer, which I find genuinely one of the most disturbing things I have encountered in a career spent looking at disturbing things, is that the physics does not have a mechanism for that information to disappear. Start here. With a principle so fundamental that every branch of physics, from thermodynamics to quantum mechanics to general relativity, either explicitly states it or implicitly relies on it. The principle is this: information is conserved. What does it mean for information to be conserved? In classical physics, it means that the equations of motion are reversible. If you know the complete state of a system at one moment, you can calculate its state at any future moment and, crucially, at any past moment. The information about where the system came from is encoded in its current state. Nothing is lost. The past is recoverable, in principle, from the present. The equations of classical mechanics are time-symmetric. They run equally well forwards and backwards. No information disappears. In quantum mechanics, the conservation of information is encoded in the unitarity of quantum evolution. The Schrödinger equation is unitary, meaning that it preserves the total probability of the wave function and, more deeply, that it preserves all the information in the quantum state. If you know the complete quantum state of a system now, the Schrödinger equation tells you the complete quantum state at any future or past time. No information is created, no information is destroyed. The quantum state at any moment contains the complete history of the system encoded in its correlations and entanglements, and that information is never lost. This is not a trivial statement. It is a deep constraint on what the laws of physics allow, and it has a direct, immediate, uncomfortable implication for the question of death. The atoms that constitute your body, the specific quantum states of every particle and every molecule in every cell, the information encoded in the configuration of your matter is subject to the conservation of information. When you die, when your biological processes cease, the atoms that were you do not disappear, they scatter, they disperse into the environment. They become part of the air, the soil, the water, the bodies of other organisms. The specific configuration that was you dissolves, but the information encoded in that configuration, the quantum states of all those atoms, does not vanish. It is redistributed, it is dispersed throughout the environment in a form that is, for all practical purposes, irretrievably scrambled. But it is not gone. The physics does not permit it to be gone. This is where most popular accounts of this idea stop. They say your atoms live on in other forms, and they treat this as a comforting thought about the continuity of matter. But I want to push harder, because I think the real implications are stranger and more significant than the atomic continuity argument suggests. The information that constitutes you is not just the positions of your atoms. It is their quantum states, their entanglements, their correlations, the specific configuration of quantum fields that implements your neural patterns, your memories, your personality, the physical substrate of whatever it is that makes you you. That information, in the rigorous quantum mechanical sense, does not disappear when you die. It becomes encoded in the quantum states of the environment, in the air molecules that carry the heat of your body as it cools, in the soil, bacteria that begin to process your remains, in the photons that scatter from your body in its last moments, in the gravitational field that your mass slightly perturbs, in every physical system that interacts with your body during and after death. The information is not concentrated anymore. It is not organized anymore. It is not doing the thing it was doing when it was you, but it exists. The quantum mechanical description of the environment after your death contains, encoded in its correlations and entanglements, the information that was you. Scrambled beyond any practical possibility of reconstruction, yes, but present. Really, physically, in principle present. Now, I want to tell you about the experiment that forced physicists to take this seriously in a context they could not avoid. The context was not death. It was black holes. And the physicist who made it unavoidable was Stephen Hawking. In 1974, Hawking showed that black holes radiate. The mechanism involves quantum vacuum fluctuations near the event horizon, pairs of virtual particles where one falls into the black hole and one escapes as real radiation. This Hawking radiation carries energy away from the black hole, causing it to slowly lose mass and eventually evaporate completely. A black hole that forms, accumulates mass, and then evaporates, leaves behind nothing but radiation. The black hole itself is gone. But here is the problem that consumed Hawking and much of theoretical physics for the following decades. If the black hole evaporates completely, what happens to the information about everything that fell into it? A star that collapsed to form the black hole, gas and dust that accumulated, perhaps a spaceship with all its instruments, its computers, its databases. All of that fell inside the event horizon. None of it can escape, because nothing can escape from inside a black hole. The information about all of it is inside the black hole. And when the black hole evaporates, where does that information go? Hawking's initial answer was that it goes nowhere. It is destroyed. The black hole evaporation is not a unitary process. Information falls in, and when the black hole is gone, the information is gone. This was called the black hole information paradox, and it was not a minor technical puzzle. It was a direct conflict between two of our most fundamental principles: quantum mechanics, which demands unitarity and conservation of information, and general relativity, which, in Hawking's calculation, allowed information to be destroyed inside black holes. This paradox occupied some of the greatest minds in theoretical physics for 30 years. Hawking himself defended the information destruction position for decades, famously betting against John Preskill that information was lost in black holes. The debate was not just about black holes. It was about whether quantum mechanics and general relativity could be reconciled, whether there was a consistent theory that respected both. It was one of the deepest conflicts in the foundations of modern physics. The resolution came gradually through a series of developments in string theory and quantum gravity that I want to sketch because the physics matters. In the 1990s, Juan Maldacena discovered a remarkable duality called the ADS-CFT correspondence between a theory of quantum gravity in a certain type of curved spacetime and a quantum field theory on the boundary of that spacetime. This duality showed that the two theories were equivalent descriptions of the same physics, and the quantum field theory on the boundary is manifestly unitary. It conserves information. Therefore, the gravitational theory in the bulk must also conserve information. Therefore, black hole evaporation must be unitary. Therefore, information cannot be destroyed. Hawking conceded the bet in 2004. He acknowledged that information is conserved, that black hole evaporation is unitary, that the information about everything that falls into a black hole is encoded in the Hawking radiation that comes out not in any recoverable, readable form, not in any way that would allow you to reconstruct what fell in from what came out without essentially infinite computational resources, but present, encoded, not destroyed. The implications of this for the question of death are direct. If the most extreme thing the universe can do to information, pulling it across an event horizon into a black hole and then evaporating the black hole over billions of years, cannot destroy that information, then certainly the biological process of death cannot destroy it. Death is not even in the same category as a black hole evaporation in terms of its capacity to scramble information. Death scatters atoms into the local environment. Black hole evaporation redistributes information across the entire thermal bath of Hawking radiation. If the latter cannot destroy information, the former certainly cannot. The information that constitutes you will survive your death. Not in any useful form, not in any form that preserves your consciousness or your memories or your personality, not in any form that is distinguishable from the information carried by the atoms of someone else who died nearby, or the information in the soil, or the information in the air, but present, not destroyed. Conserved, in the only sense the physics can give that word. Now I want to take you somewhere more speculative, but I think more important, because the conservation of information is a necessary but not sufficient condition for what I really want to say. The sufficient condition requires something else, something that follows from the block universe picture of space-time that we discussed in an earlier video, and from the many worlds interpretation of quantum mechanics that we discussed in the previous video. If the block universe is real, if space-time is a four-dimensional structure in which every event at every time is equally present as a location in that structure, then the events that constituted your life, the specific configurations of matter and energy that implemented your experience, are permanent features of that structure. They are not in the past in the sense of being gone. They are in the past in the sense of being at a different temporal location in the four-dimensional block. As I argued before, the event of your birth is still happening for observers in distant galaxies who have not yet received the light from it. By exactly the same logic, every moment of your life is still present somewhere in the block, accessible to reference frames that are appropriately situated relative to Earth. Your death, when it comes, will be an event in the block, an event at a specific space-time location. And from the perspective of the block, that event will be surrounded by the events of your life. The moments before your death, the years of your existence, will be adjacent to it in the four-dimensional structure. Not more or less real than it, not gone, present, as real as the moment of your death, as present to some reference frame as the moment of your death. This is not comfort in the usual sense. The inaccessibility is real from your subjective experience. Moving forward along your world line, the moments of your life will recede and your death will approach, and after it there will be no more of your subjective experience. That asymmetry is real, and I am not going to pretend it is not. but the ontological status of those moments, their reality in the structure of space-time, is not diminished by their inaccessibility from your future. They exist. They are part of the block. They are as permanent as any other feature of physical reality. And in the many worlds picture, your death is an event that happens in some branches of the universal wave function and not in others. In branches where your death occurs at one time, there are branches where it does not occur at that time, where the quantum fluctuations that contributed to the biological failure went differently, where you are still alive. The branching structure of the universal wave function means that there is no single fact about when you die. There is a probability distribution over branches, each with its own history. In every branch, in every version of the universal wave function that contains something like you, the information that constitutes you is conserved. None of those branches involves the destruction of your information. All of them involve its dispersal into the environment in different ways at different times. Now I want to address directly the most important question, the one that I think is really behind the question of what happens to us when we die. Not what happens to our atoms, not what happens to the information in the physics sense, but what happens to the experience, to the subjective quality of being alive, to the what it is like to be you. This is the hard problem of consciousness, which I discussed in the context of the universal wave function in the previous video, and I want to be completely honest about where physics stands on it. Physics does not know what consciousness is. It does not know whether consciousness is a physical process in the sense of being fully implemented by the physical configuration of matter and energy, or whether it has some additional non-physical component that physics cannot describe. The hard problem of consciousness, the question of why physical processes produce subjective experience, is genuinely unsolved. Nobody has a satisfying answer to it. What physics can say is this: every experience you have ever had has been correlated with a specific physical state of your brain. Alter the physical state, alter the experience. Damage specific brain regions, lose specific capabilities. Anesthesia disrupts neural activity. Experience ceases. The correlation between physical brain states and conscious experience is overwhelming and well established. This does not prove that consciousness is nothing more than physical brain activity, but it establishes that the physical configuration is necessary for the experience. When that physical configuration disperses at death, when the neural patterns that implemented your consciousness are scattered into the environment, the specific process that was generating your experience stops. Whatever consciousness is, the physical substrate that it required is no longer organized in the way it was organized when you were alive. If consciousness requires that organization, it stops with the organization. If it does not require that organization, if it has some other basis, then physics does not have the tools to say what happens to it. What physics cannot say is that consciousness is destroyed. Not because it knows that consciousness survives, but because it does not know what consciousness is, and therefore cannot know what its physics entails. The hard problem is not just philosophically interesting. It is the specific gap in our knowledge that prevents us from giving a complete physical account of death. Let me tell you about something that I think is one of the most physically interesting aspects of this question, and that gets almost no attention in popular discussions of death and physics. It involves the thermodynamic arrow of time and what it tells us about the relationship between life and death. The second law of thermodynamics says that entropy, the measure of disorder in a physical system, tends to increase over time in isolated systems. The universe moves from lower entropy to higher entropy, from organized to disorganized, from concentrated to dispersed. This is the thermodynamic arrow of time. The reason the past feels different from the future. The reason a shattered glass does not spontaneously reassemble. The reason the universe has a direction. Life is, from a thermodynamic perspective, a local and temporary violation of this tendency. Not a real violation. The second law allows local decreases in entropy as long as greater increases occur elsewhere. But a striking local exception. Living organisms maintain low entropy configurations, highly organized structures, far from thermodynamic equilibrium, by consuming energy from their environments and exporting entropy. You are a low entropy island in a high entropy sea, maintained by the constant throughput of energy from the food you eat and the oxygen you breathe. Death, from this perspective, is the termination of the process that maintained the low entropy configuration. When you die, when the biological machinery that kept your organization intact stops functioning, your entropy increases. The specific low entropy configuration that was you begins to dissolve into the higher entropy configuration of the surrounding environment. This is what biological decomposition is. Not the destruction of your information, but its dilution into the entropy of the world. But here's the thing about the second law that I want you to hold. The second law is statistical. It describes the overwhelmingly probable behavior of systems with large numbers of degrees of freedom. It does not describe a fundamental physical law in the same sense that quantum mechanics or general relativity does. There is no operator in the fundamental equations of physics that enforces entropy increase. The increase of entropy is emergent, a consequence of the overwhelming statistical improbability of low entropy configurations arising spontaneously in a large system. This means that the thermodynamic description of death, the dissolution of a low entropy configuration into the environment, is not the fundamental physical description. It is the macroscopic statistical description. The fundamental description is the quantum mechanical one, the unitary evolution of the quantum state of your atoms and their environment, conserving all information, redistributing it into the correlations and entanglements of an ever larger system. At the macroscopic level, you die and decompose. At the quantum mechanical level, the information that was you becomes entangled with the universe in an irreversible but non-destructive way. Both descriptions are true. They describe the same physical process at different levels, but they have very different implications for the question of what death means. The macroscopic description says you are gone. The quantum mechanical description says your information is dispersed but present, encoded in the quantum state of everything your body has interacted with, propagating outward at the speed of light as the photons that carried information about your existence scatter into the cosmos. I want to sit with that for a moment. The photons that have scattered from your body over the course of your life are right now moving outward through space at the speed of light, carrying information about you in their quantum states. They will continue to do so long after you are dead. The gravitational field that your mass has perturbed, however slightly, will continue to be perturbed in ways that encode information about your existence long after you are gone. The quantum states of the atoms you have breathed and eaten and shed carry correlations with the atoms that constitute you, correlations that persist even as those atoms are dispersed into different environments. You are, in the quantum mechanical sense, already spreading into the universe, already leaving traces that will outlast your biological existence, already entangled with systems that extend far beyond your body. The death of your body is not the end of the physical process that is you. It is the termination of one particular mode of that process, the low entropy organized mode, and the transition to another mode, the dispersed, high entropy, but informationally persistent mode. Now I want to tell you about the specific calculation that I think is most relevant to this question, and that is rarely discussed in this context. It is a calculation about the Poincaré recurrence time of the universe. Henri Poincaré proved in 1890 that any bounded dynamical system will, given enough time, return arbitrarily close to its initial state. The system may wander far from its starting point, may explore a vast portion of its available phase space, but eventually, if the system is bounded and the laws of mechanics are reversible, it will come back. Arbitrarily close? Not exactly, but within any epsilon you choose. Applied to the universe, this theorem implies something extraordinary. If the universe is finite and its evolution is governed by reversible laws, which quantum mechanics requires, then the universe will eventually return to a state arbitrarily close to any past state, including the state it was in when you were alive, including a state in which a configuration very similar to you exists again, with something very like your memories and your experiences and your consciousness. If consciousness is a physical process, the Poincare recurrence time for the observable universe is unimaginably vast. Numbers so large that writing them out in standard scientific notation would require more digits than there are atoms in the observable universe. The recurrence will not happen in any cosmologically meaningful time scale. The heat death of the universe, the final equilibrium state toward which entropy increase is driving everything, will occur long before any significant recurrence. And we do not know whether the universe is finite or whether Poincaré's theorem applies to it in the relevant sense. But the mathematical possibility is not nothing. It is a statement about what the laws of physics permit. And what they permit, given enough time and the right conditions, is the reemergence of configurations like you from the thermal noise of a universe that has never destroyed the information that constituted you. I am not telling you this as a promise. I am not telling you that you will live again, that consciousness persists, that death is an illusion. I am telling you that the physics is stranger than the intuition, that the laws governing the universe do not contain a mechanism for destroying the information that constitutes a living system, that the block universe preserves the events of your life as permanent features of a four-dimensional structure, that the universal wave function never collapses, the branch that contains you into nothing, and that given timescales that exceed any human comprehension, the configuration that implements your experience is not ruled out from recurring. What I think is most important is not the specific conclusions, some of which are deeply speculative, but the frame that physics provides for thinking about death is fundamentally different from the frame that intuition provides. The intuitive frame says death is annihilation. The information, the experience, the self is extinguished, gone. The void after death is complete and final. The physical frame says something more complicated. Something about dispersal and conservation and permanence in the block and unitarity in the quantum evolution and the overwhelming improbability but not impossibility of recurrence. The physical frame does not provide comfort in the way that religious or philosophical frameworks might. It does not tell you that you will be reunited with people you have lost. It does not tell you that consciousness persists in some recognizable form after biological death. What it does is refuse to endorse the annihilation narrative. It says that the information is not destroyed. It says that the moments of your life are permanent features of the space-time block. It says that the quantum state of the universe contains, encoded in its correlations, the physical record of your existence. It says that death is a transition, not an ending, in the only senses that physics can give to those words. I find that simultaneously less comforting and more interesting than the alternative. Less comforting because it does not promise survival of experience. More interesting because it points toward a picture of reality in which the boundaries we draw between being and not being are not fundamental features of physics, in which the line we draw between alive and dead, between present and past, between existing and having existed, is a line drawn by thermodynamics and biology and human intuition, but not by the fundamental equations. The fundamental equations do not draw that line. The Schrödinger equation does not have a term that describes the destruction of a configuration. The block universe does not have a mechanism for removing events from the four-dimensional structure. The conservation of information does not have an exception for biological death. Physics has looked at death carefully and precisely in every domain it has examined. And what it has found is not annihilation. What it has found is transformation, dispersal, persistence in a different mode. The kind of change that feels from the inside of a biological system like ending, but that looks from the outside of a physical description like the same conserved, unitary, block permanent information redistributing itself into the universe that always contained it. Physics has never observed the moment of death because there is no moment at which the information that constitutes a living system is destroyed. There is a moment at which the organized, low-entropy configuration that implements consciousness stops functioning. But the information does not go anywhere. It was always part of the universe. It remains part of the universe in different forms, at different locations, encoded in different correlations, but present. That is the most disturbing thing physics has found. Not that death is an illusion, but that annihilation is. The universe does not destroy what it contains. It only transforms it. And what it transforms are configurations of information that were, for a brief time, organized in a way that allowed them to experience themselves as alive. I am one of those configurations. You are one of those configurations. And whatever we are, the physics says we have never been and can never be nothing. Go outside tonight, breathe the air. The oxygen molecules entering your lungs carry quantum correlations with the atoms that produce them, atoms that were once inside stars, atoms that have been part of other organisms, atoms that carry in their quantum states the faint physical record of everything they have ever interacted with. You are breathing history. You are inhaling the dispersed quantum record of processes that happened before the Earth existed. And when you exhale, you are contributing to that record. Adding your information to the quantum state of the world, extending the physical trace of your existence into the air, into the light, into the field that permeates everything, you are already more than your body. You have always been more than your body. The physics says so. Not because you are special, but because nothing in the universe is just itself. Everything is entangled with everything it has touched. And what you have touched, what has touched you, extends further than you know and persists longer than you fear. That is not nothing. That, I think, is worth knowing. If this landed for you, if it changed something in the way you think about what ends when a life ends, tell me in the comments. Tell me what piece of this you find most difficult and what piece you find most true. Tell me what the conservation of information means to you when you apply it personally. These conversations shape what comes next. And subscribe if you want to keep going to the places where physics asks the questions we are afraid to ask ourselves.